Greetings, folks. Joseph Kursky here with you to explore with you oceans as regions with spatial technology. As you know, nearly 71% of the world is covered by oceans. So for centuries, and even often in our current era, oceans are mapped as a uniform color, green or blue, or another color, and are not really thought of as regions, but as geographers and oceanographers are discovering, oceans are as dynamic as land. Many would argue even more so, and examining oceans as regions is possible with spatial technology. Let's do exactly that. Let's examine ecological marine units data as part of our investigation. In many respects, the ocean is the last frontier on Earth, right? Much about them remains unknown and unmapped, but given the importance of oceans to the carbon cycle, the food chain, biodiversity, climate, and many other Earth systems, not to mention economic systems, right? Shipping and so on and so forth, there is a growing sense that this needs to change. Given the vastness, the changing nature, and the 3D nature of the oceans, spatial technology is turned to as a solution for understanding and mapping the oceans. The Ecological Marine Units map has been created to portray a systematic division and classification of physiographic and ecological information about features in the ocean. A statistical clustering methodology was also developed for identifying the physiographic structure of the water column based initially on temperature, salinity, dissolved oxygen, and nutrients. That is, the usual suspects that will likely drive ecosystem responses. Now, this methodology was developed by Esri's Kevin Butler and vetted by distinguished spatial statistics professor Noel Cressy of the University of Wollongong in Australia. Good day. That information was connected to species distributions, initially from the Ocean Biographic Information Systems, or OBIS, biogeographic realms, and seabed habitat and biotopes representing the response of these ecosystems to the physical setting. For example, the biological distribution response to ocean acidification. The Group on Earth Observations, or GEO, officially commissioned the project as a means of developing a standardized, robust, and practical global ecosystems classification and map for the oceans. GEO is a consortium of almost 100 nations collaborating to build the Global Earth Observation System of Systems, GEOSS. EMU project, or Ecological Marine Units, is seen by GEO as a key outcome of the GEO Biodiversity Observation Network and the new GI-14 GEO Global Ecosystems Initiative. For more information about what you're going to be working with, see this document. Okay, using the Ecological Marine Units as an investigative tool. Begin your investigation of the Ecological Marine Units, one of my favorite data sets ever, with this Explorer map. Click anywhere on the map and you will observe a graph to the right of the map with ocean water variables displayed in graph form by depth. Clicking on the temperature profile title of the graph yields the other graphs, nitrate, salinity, and others, available for that location. Isn't this amazing, folks? Absolutely stunning. Pan to Australia and click a point off the shore of New South Wales or Victoria. The map should look similar to this. See, you've got the column, you've got all the information right here that you can investigate and compare to other columns. Now, adding to the complexity of understanding the ocean's regions is that for any one location, the regions overlay, or more accurately, underlay, right, each other. On land, while elevation, sure, it influences the plant and animal life, climate, water, soil, and vegetation, to name a few, each location on land is represented by a single region. But in the oceans, the regions sit, or slosh, I guess is a better word, atop each other. Consider the example above that you're looking at right here. Off the coast of Australia lies EMU Region 11, northern and southern subtropical epipelagic. Epipelagic refers to the part of the oceanic zone into which enough light permeates for photosynthesis. At the location clicked, it is 275 meters thick. Underneath this is EMU 8, the subantarctic, North Atlantic, and North Pacific epipelagic. Extending another 275 meters, and underneath that is EMU 36, the Atlantic, Subantarctic, and North Pacific subtropical bathypelagic region. Bathypelagic, from Greek, well, I can't pronounce it, is deep, okay? It refers to that part of the pelagic zone that extends from a depth of 1,000 to 4,000 meters below the ocean surface. Here, no primary production of plant life exists, so all creatures that live there are carnivorous, eating each other or feeding on carcasses that sink down from above. And underneath this are emus 37 and 14. For a two-dimensional cross-section with these zones labeled by depth, see this figure in this metadata booklet. Remember, the metadata is the data about the data, about the map in this case. Now let's examine ecological marine units around the world. Use this table right here in the metadata booklet to compare the Emu 11 to the other emus in terms of depth, temperature, dissolved oxygen, nitrate, phosphate, and silicate. Now examine the map on the page 12 and 13 of this booklet and note the distribution and spatial patterns of the ecological marine units around the world. Which would you say is the largest in area? Be careful. Emus 19 and 31 in the Southern Ocean may look like the largest, but remember that the map projection actually matters here. The map projection may distort the area of land and water near the poles. Scroll down to page 20 and 21, which is page 11 and 19, 11 of 19 PDF, and examine the map of Emu 11, reproduced here, that was present at the surface off the southeast coast of Australia, the northern and southern subtropical epipelagic. How would you describe the spatial distribution of this ecological marine unit? Note the equatorial location of emus 18 and 24 and predict their mean temperature compared to other emus. Scroll back up to the table. Was your hypothesis correct? Note the high amount of dissolved oxygen contained in ecological marine units 5 and 16. Now, knowing that cold water can hold more dissolved oxygen than warm water, predict the location of emus 5 and 16. Scroll back up to the map. Was your hypothesis correct? Now let's examine Australia ecological marine units, folks. Go back to the interactive ecological marine units map. Begin again by clicking off the coast of Southeast Australia. Gradually move and click northward along the coast, along the east coast, observing the graph that shows at the right. What do you notice about water temperature as you move north? Why? How and why does the dissolved oxygen change? So if you're teaching primary level, if they can just note that it gets warmer as you go toward the equator, great. Lesson accomplished, right? Mission accomplished. But if they're secondary, you might want to get them into, okay, why do we care about dissolved oxygen anyway? And what is dissolved oxygen? Now, always be critical of the data. That's a theme that runs throughout this spatial technology module. Now, emus, ecological marine units, being a wonderful data set, it's still no exception. You still need to be critical of it. Keeping with our theme of being critical of the data, there is no water quality measurement buoy or set of ships at every square meter on the surface of the ocean with a tether extending down to the ocean floor. It just doesn't exist. Rather, the data are sampled as follows. The fundamental approach undertaken was to stratify the ocean into physically and chemically distinct areas. The stratification was produced from an unsupervised statistical clustering of data from NOAA's 2013 World Ocean Atlas version 2. The data used in the clustering represent 57-year average values for temperature, salinity, dissolved oxygen, nitrate, phosphate, and silicate. Approximately 52 million ocean data points representing the entire water column were sampled, okay? The horizontal resolution of the data is 1/4 of a degree, or approximately 27 kilometers near the equator. The depth intervals are variable from 5 meters near the surface to 100 meters in the deeper ocean, up to over 2,000 meters deep, for a total of 102 depth values. The marine units were produced from a k-mean statistical clustering of the point data, resulting in 37 distinct clusters. Each cluster, or ecological marine unit, is a physically and chemically distinct volumetric region, right? It is a column. Thus, the data were rigorously produced, but zoom in until you see the data points as shown here. You can now see the data points spaced at 1/4 degree latitude and longitude apart. In the same way on land, you examined a sample grid of data points in another part of this module from the Degree Confluence Project to examine physical and cultural regions. So no exception here. It's a sample, but it's wonderful data. Now let's dig deeper. To dig deeper, Literally, let's examine some of the 3D views in this story map of the ecological marine units. Scroll down to additional samples at the end and examine the areas offshore from Ireland and offshore from Central America. This might provide a better sense of the 3D nature of each column of data across the ocean. Go ahead and skim the research document to discover how the EMU data can be used by those using spatial technology. And to examine the data in 3D in a spatial technology environment, it requires the use of a desktop GIS called ArcGIS Pro. Good news, with your ArcGIS Online school account, you can also get access to ArcGIS Pro. Think about that for later if you truly want to dig deeper. Well, congratulations. You actually have done some deep, get it, deep ocean investigation of ecological marine units. And giving your students a sense of, the oceans are dynamic and they have spatial characteristics over X, Y, right, across the surface, but also in their depth. So they're a diverse, highly in need of protection part of our planet. And you've investigated it in some key ways with spatial technology. Thanks.